Welcome to tonight's journey with the Curious Owl. Before we begin, I want to invite you to settle in, perhaps adjusting your pillow, letting your shoulders drop, allowing your breathing to find its own gentle rhythm. If you find value in these quiet explorations of our world, consider leaving a like or subscribing to this channel or sharing this with someone who might enjoy drifting off to sleep while learning something new. I want you to know that there will be no advertisements interrupting this audio, nothing to jar you from your rest. And if you'd like, when morning comes, perhaps you'll leave a comment sharing what you enjoyed or how we might make these journeys even better. Thank you, truly, for choosing to spend this time with the Curious Owl. Now, let's begin. Tonight, we're going to explore something so vast, so fundamental to our existence, that we often forget just how remarkable it truly is. We're going to consider the ocean, not as a backdrop, not as a vacation destination, but as the dominant force that shapes our world. When you imagine Earth from space, what comes to mind? Most of us picture that famous photograph, the one showing a sphere of deep blue, interrupted here and there by swirls of white cloud and patches of brown and green land. That blue isn't an accent. It isn't decoration. It is quite literally what our planet is made of. The Earth is fundamentally a marine world. The global ocean covers approximately 71% of the planet's total surface area. Think about that for a moment. Nearly three-quarters of everything you could touch, if you were somehow able to reach down from space, would be water. This vast expanse totals roughly 360 million square kilometers. It's a number almost too large to hold in your mind. But what it means, in simpler terms, is that the ocean dictates what Earth looks like. It determines our physical appearance as a planet, and it serves as the primary medium through which geological and biological processes unfold. Because the ocean is so pervasive, covering so much of the globe without interruption, it functions as a continuous planetary skin. It bridges the gap between the lithosphere below, the solid rocky crust we call land, and the atmosphere above, that thin envelope of gases we breathe. The ocean ensures that Earth remains a cohesive, interconnected system, rather than just a collection of isolated land masses drifting separately through space. Now, when we talk about water on Earth, it's important to understand just how concentrated it is in these oceanic basins. The distribution isn't even. It's overwhelmingly skewed. Salt water accounts for approximately 97% of the planet's total water supply. 97%. The remaining 3%, that's fresh water. And even within that small fraction, the vast majority is locked away in polar ice caps and glaciers, or stored deep underground in aquifers far from the surface where life congregates. This means that the liquid water we see in rivers, in lakes, in the clouds, drifting overhead, the water most accessible to terrestrial life, to us, represents less than 1% of Earth's total hydrosphere. Less than 1%. It's a humbling thought, isn't it, that the water we drink, the water that fills our reservoirs and runs through our cities, is such a vanishingly small portion of the whole. The ocean, then, is the primary reservoir. It holds nearly all of the planet's life-sustaining fluids. But the ocean does far more than simply exist as a storage tank for water. It actively shapes the world we live in. And one of the most important ways it does this is through temperature regulation. Water has a high specific heat capacity. What that means, in practical terms, is that it takes a tremendous amount of energy to change the temperature of water, even slightly. The ocean, with its vast volume, acts as a massive thermal reservoir. It absorbs enormous quantities of solar radiation without experiencing rapid changes in temperature. This is what we call thermal inertia. Imagine for a moment what Earth would be like without this buffering effect. Without the ocean's ability to absorb and hold heat, our planet would experience wild temperature swings between day and night. Scorching heat when the sun was overhead, plummeting cold as soon as darkness fell. The seasons would be far more extreme, perhaps unbearably so. But the ocean moderates all of this. It absorbs heat during the day and releases it slowly at night. It stores warmth during summer and releases it gradually through the colder months. And it doesn't just do this locally. Through a global network of currents, the ocean transports this absorbed thermal energy from the equatorial regions, where sunlight is most intense, toward the poles, where it is scarce. This redistribution of heat across the globe maintains the temperate conditions necessary for diverse ecosystems to thrive. It's why places like Western Europe, which share the same latitude as frigid parts of Canada, enjoy much milder winters. The ocean carries warmth to them. In the context of contemporary environmental shifts, the changes we're witnessing in our climate, the ocean serves as a critical buffer in another way. It absorbs over 90% of the excess heat trapped in the climate system due to increased concentrations of greenhouse gases. 90%. Most of the warming that human activities have caused isn't, at least not yet, showing up in the air around us. It's being sequestered in the ocean. This absorption occurs primarily in the upper layers of the water column, in the top few hundred meters where sunlight penetrates and where the water is most directly exposed to the atmosphere. But gradually, through vertical mixing and through processes called downwelling, that heat penetrates deeper into the ocean's interior. While this process slows the rate at which the atmosphere warms, giving us, in a sense, more time, it comes with consequences. The increase in ocean heat content alters the density of seawater. Warmer water expands, taking up more volume. This is one of the primary drivers of rising sea levels. And there's more. As the ocean warms, it affects the great conveyor belt of currents that circulate water around the globe. These thermohaline circulation patterns, driven by differences in temperature and salinity, can strengthen in some areas, weaken in others, or shift their pathways entirely. These changes, subtle as they may seem in the moment, ripple through ecosystems and weather patterns in ways we're only beginning to understand. Beyond regulating temperature, the ocean functions as a primary carbon sink. It absorbs roughly 1/4 to 1/3 of the carbon dioxide emitted into the atmosphere. This includes carbon from natural sources, like volcanic eruptions, and the respiration of living organisms, but also from anthropogenic sources, the burning of fossil fuels, deforestation, industrial processes. When carbon dioxide enters the ocean, it doesn't just sit there unchanged. It dissolves into the surface waters and undergoes a series of chemical reactions. One of the first is the formation of carbonic acid. This is the same weak acid that gives carbonated beverages their slight tang. The gas exchange between the atmosphere and the ocean is governed by what's called the difference in partial pressure. If there's more carbon dioxide in the air than in the water, the gas will move from air to sea until an equilibrium is reached. Once the carbon is sequestered in the water, it can be transported to the deep ocean through various mechanisms. One is called the biological pump. This is where living organisms, phytoplankton, zooplankton, shellfish, incorporate carbon into their tissues and shells. When they die, they sink, carrying that carbon with them into the depths. Another mechanism is the solubility pump, which simply refers to the fact that cold water can hold more dissolved gas than warm water. As surface water cools, it sinks, carrying dissolved inorganic carbon into deep water layers. But there's a darker side to this carbon absorption. When carbonic acid forms, it makes the ocean more acidic. Over the past 2 centuries, the ocean's pH has already dropped measurably. This is problematic for organisms that build shells or skeletons out of calcium carbonate, corals, mollusks, certain plankton. In more acidic water, it becomes harder for them to construct these structures, and in some cases, existing structures begin to dissolve. It's a quiet crisis unfolding beneath the surface, one that could reshape marine ecosystems in profound ways. The ocean is also the central engine of the global hydrological cycle, the continuous movement of water through Earth systems. Most of the water vapor in the atmosphere originates from the evaporation of seawater. Solar energy fuels this process, providing the energy needed to break the bonds between water molecules and lift them into the air. Crucially, when seawater evaporates, the salts are left behind. Only the water molecules transition into vapor. This natural distillation process provides the moisture necessary for precipitation over the continents. And this cycle is not just about moving water from one place to another. It's a massive heat exchange mechanism. When water evaporates, it stores latent heat, energy that's hidden, tucked away in the molecular structure of the vapor. Later, when that vapor rises, cools, and condenses into clouds, or eventually into rain, that stored energy is released into the atmosphere. This release of latent heat is a major driver of weather systems, of storms, of the winds that blow across the surface of the planet. The ocean, through this constant exchange of mass and energy with the atmosphere, regulates global weather patterns and ensures the replenishment of freshwater resources on land. Now, let's talk about something the ocean is famous for: its saltiness. The average salinity of the global ocean surface is approximately 35 parts per thousand. That's a measurement indicating that in every kilogram of seawater, a little more than a liter, there are roughly 35 grams of dissolved inorganic solids. Most of these dissolved substances are sodium and chloride ions, which combine to form common table salt. But there are trace amounts of many other elements as well: magnesium, sulfur, calcium, potassium, and even exotic elements like gold, though in concentrations far too low to be worth extracting. This concentration remains remarkably consistent across the open ocean. Dip a cup into the Pacific, the Atlantic, the Indian Ocean, and you'll find roughly the same salinity. This stability provides a consistent chemical environment, one that influences the density of seawater, its electrical conductivity, and the osmotic pressure that marine organisms must contend with. But while the average is stable, local salinity does fluctuate. In most places, it falls somewhere between 32 and 37 units on the practical salinity scale. These variations are driven by the local balance between the removal and addition of fresh water. Think of it as a tug of war. On one side, you have processes that remove fresh water, evaporation, which lifts pure water into the atmosphere and leaves the salt behind, and the formation of sea ice, which also excludes salt as it freezes, concentrating what's left in the liquid water below. Both of these processes increase salinity. On the other side, you have processes that add fresh water, diluting the salt concentration. Heavy rainfall, the melting of glaciers, and the discharge of massive river systems all introduce fresh water into the ocean. Where great rivers meet the sea, the Amazon, the Congo, the Ganges, the salinity drops noticeably. You can sometimes track these freshwater plumes extending hundreds of kilometers out into the open ocean. But where did all this salt come from in the first place? The primary source is the chemical and physical weathering of rocks on the Earth's continents. Rainwater, which is slightly acidic due to dissolved carbon dioxide, falls on the land. As it trickles through soil and over stone, it interacts with minerals. It breaks them down, ion by ion. These ions, sodium, chloride, calcium, magnesium, are carried away by runoff into streams, then into rivers, and eventually into the ocean basins. This has been happening for billions of years. Rivers have continuously transported dissolved minerals into the sea. It's a slow process, imperceptible on human timescales, but over geological time, it has loaded the ocean with salt. There are additional contributions too. Hydrothermal vents on the seafloor release minerals directly from the Earth's interior into the water column. Volcanic activity, both underwater and on land, adds its own chemical signature. All of these sources, acting together, have made the ocean what it is, a vast saline solution. Salinity levels are notably higher in certain parts of the world. In the subtropical regions, roughly between 20 and 30 degrees latitude in both hemispheres, you find what are sometimes called the evaporation belts. These are zones where the sun beats down intensely, where dry air masses prevail, and where evaporation rates are exceptionally high. The rate of evaporation here significantly exceeds the rate of precipitation. Fresh water is constantly being stripped from the surface and lifted into the atmosphere, leaving behind a more concentrated brine. The water becomes denser and saltier. Often, these high salinity surface waters eventually sink and circulate through the deep ocean, contributing to the global system of currents. In contrast, you find lower salinity levels in equatorial regions, in high-latitude polar zones, and along coasts near major river mouths. In the tropics, frequent and heavy rainfall, associated with a feature called the intertropical convergence zone, adds vast quantities of fresh water to the surface. Similarly, in polar regions, the seasonal melting of ice and the discharge of large rivers, think of the massive rivers flowing into the Arctic from Siberia, introduce enormous volumes of fresh water. These inputs maintain a lower salinity profile compared to the open subtropical oceans. On a global scale, over geological time, the ocean's average salinity is in what scientists call a steady-state equilibrium. This doesn't mean nothing is changing. It means that the inputs and outputs are balanced. The total amount of salt being added to the ocean from continental weathering and hydrothermal activity and volcanic eruptions is roughly equal to the rate at which salts are being removed. And yes, salts are removed. They're deposited in evaporite minerals, thick layers of salt left behind when ancient seas dried up. They're buried in sediments on the seafloor. They're drawn down into the Earth's mantle when oceanic plates subduct beneath continental ones. This balance ensures that while local salinity may shift with the seasons or the decades, the overall chemical composition of the global ocean has remained relatively stable for hundreds of millions of years. The presence of dissolved salts fundamentally alters the physical properties of water. One of the most noticeable changes is to the freezing point. Pure water, the kind you might distill in a laboratory, freezes at 0 degrees Celsius. But typical seawater, with its 35 parts per thousand of salt, requires temperatures to drop to approximately minus 1.9 to minus 2 degrees Celsius before ice crystals can form. The salt ions interfere with the water molecule's ability to organize into a rigid hexagonal lattice, the structure that defines ice. And here's something interesting. As seawater freezes, the salt is excluded from the crystal structure. Ice is almost pure water. The salt gets pushed out, creating pockets of highly concentrated brine in the surrounding liquid. This brine is denser than normal seawater, and it sinks. This process, called brine rejection, plays a vital role in driving deep ocean circulation, particularly in polar regions where sea ice forms each winter. Salinity also affects the transition from liquid to gas, raising the boiling point of water slightly. This phenomenon, known as boiling point elevation, occurs because the dissolved salt particles lower the vapor pressure of the liquid. It takes more thermal energy for the water molecules to break free and escape into the atmosphere as steam. While this elevation is relatively small at standard oceanic salinities, maybe a fraction of a degree, it's a critical factor in certain thermodynamic calculations and in understanding hypersaline environments like the Dead Sea or salt flats where evaporation has concentrated the salts to extreme levels. When seawater evaporates, something remarkable happens. Only the water molecules transition into a gaseous state. The dissolved salts are left behind in the liquid phase. This selective process is the fundamental mechanism that maintains the ocean's saltiness over eons. The sun drives the water cycle, lifting pure water into the atmosphere, where it eventually falls as fresh rain or snow. But the salts remain sequestered in the ocean basins. Over time, this constant distillation concentrates the salt. Without the removal processes we discussed earlier, burial in sediments, subduction, evaporite formation, the ocean would become saltier and saltier with each passing millennium. The density of seawater is a fundamental driver of global ocean dynamics, and density is directly proportional to salt content. As the concentration of dissolved salts increases, the mass of the water per unit volume also increases. Saltier water is heavier than fresher water at the same temperature. This might seem like a small difference, something you'd barely notice if you were swimming, but it creates a gravitational instability. Heavier water seeks a lower level. It wants to sink. This initiates a downward vertical movement, and this process is essential for the formation of deep water masses, which act as the subsurface engine for global circulation. Temperature and salinity function together as the primary variables in what's called the equation of state for seawater. They collectively determine its density. They're independent properties. You can have cold fresh water, or cold salty water, or warm salty water, and so on. But their combined effect dictates whether a parcel of water will float or sink. Cold salty water is the densest. Warm fresh water is the most buoyant. And small fluctuations in either variable can trigger significant shifts in water movement. Imagine a surface current flowing through a region where evaporation is intense. As fresh water is removed, the salinity increases slightly. Or imagine that same current moving into a region where the air temperature drops. The water cools. Either of these changes, or both together, can reach a tipping point where the water mass loses buoyancy and begins its descent into the deep ocean. The ocean's vertical structure is incredibly sensitive to these differences. A variation of only 2 parts per thousand, shifting from, say, 34 to 36 grams of salt per kilogram of water, is sufficient to create a density gradient that drives massive volumes of water to sink or rise. These subtle contrasts are responsible for the complex layering you find in the ocean. Distinct rivers of water, each with its own temperature and salinity signature, flow over and under one another without mixing. They maintain their identity over thousands of miles. Point. Thermal changes typically cause more immediate and significant shifts in volume and density. This is why the warmest waters are almost always found at the surface. They create a stable, buoyant layer that resists mixing with the colder, denser waters residing just a few hundred meters below. But there are places where both low temperatures and high salinities coincide. These are the sites where the densest water on Earth is formed. The North Atlantic is one such place. Around the Antarctic continent is another. In these regions, surface waters are chilled by frigid winds. Their salinity is increased through brine rejection as sea ice forms. The result is ultra-dense water, heavy enough to sink all the way to the sea floor. This is how deep water and bottom water are created, the water masses that fill the world's oceanic basins at depth. These deep-moving masses are also the primary mechanism by which oxygen is transported from the surface, where it's abundant, to the deep sea abyss, where it would otherwise be absent. Vertical stratification in the ocean is often marked by sharp transition zones. One of these is the halocline, a region where salinity levels change rapidly over a relatively small change in depth. The halocline acts as a physical barrier to vertical mixing. In the Arctic Ocean, for example, there's a strong halocline that prevents the deeper, warmer, saltier Atlantic water from reaching the surface. If it weren't for that barrier, the Arctic sea ice would melt much more quickly. These layers effectively partition the ocean into distinct functional zones, each with its own chemical and biological characteristics. A similar feature is the thermocline, a transition layer defined by a rapid decrease in temperature with increasing depth. Just below the sun-warmed surface layer, the thermocline marks a region of dramatic cooling. Temperatures can drop many degrees Celsius over just a few hundred meters. This layer separates the well-mixed, turbulent surface waters from the calm, isothermal, deep ocean. The strength and depth of the thermocline vary seasonally and geographically. It's most pronounced in the tropics, where the surface is very warm. It's nearly absent in polar regions, where the entire water column is consistently cold. When the gradients of temperature and salinity align, they create a pycnocline, a region where water density increases sharply with depth. The pycnocline is perhaps the most significant structural feature of the ocean's interior. It acts as a ceiling for deep water and a floor for surface water. Because it's very difficult for water to move vertically through a strong pycnocline, it limits the exchange of nutrients from the deep sea to the surface, and the exchange of gases from the surface to the deep. This fundamentally shapes the productivity of marine ecosystems. Where the pycnocline is weak or disrupted, nutrients can rise and life blooms. Where it's strong and stable, the surface can become a biological desert. Now, let's turn our attention to the ocean basins themselves, the great divisions of the global sea. The Pacific Ocean is the preeminent geographic feature of our planet. It occupies a vast basin covering approximately 165 million square kilometers. This single body of water represents about one-third of the Earth's total surface area. Think about that. One ocean covering a third of the entire planet. It's larger than all the world's land masses combined. The Pacific stretches from the Bering Strait in the Arctic Circle down to the 60th parallel south, where it meets the Southern Ocean. Because of its immense size, it contains nearly half of the Earth's free water. It hosts the deepest points on the planet, including the Mariana Trench, which plunges more than 11 kilometers below the surface. Its scale is so vast that it significantly influences global atmospheric circulation. It's the primary engine for phenomena like El Niño, an oscillation in sea surface temperatures that can alter weather patterns across the entire globe, bringing droughts to some regions and floods to others. The Atlantic Ocean is the second largest basin, covering roughly 20% of the Earth's surface. It occupies an elongated S-shaped basin bounded by the Americas to the west and Europe and Africa to the east. The Atlantic is geologically young compared to some other ocean basins. It's characterized by the Mid-Atlantic Ridge, a massive underwater mountain range where tectonic plates are pulling apart. Magma rises from the mantle, cools, and solidifies, creating new seafloor. This process, called seafloor spreading, is slowly pushing the continents on either side farther apart, at a rate of a few centimeters per year. The Atlantic serves as a critical corridor for what's sometimes called the global conveyor belt, the system of deep ocean currents that circulates water around the planet. It's the primary site for the formation of North Atlantic deep water, one of the densest water masses in the world. In the far north, in the waters between Greenland, Iceland, and Norway, surface water cools and sinks, beginning a journey that will take it south along the floor of the Atlantic, around Africa, into the Indian Ocean, and eventually into the Pacific. This conveyor belt drives much of the world's thermohaline circulation, redistributing heat, salt, and nutrients across the globe. The Indian Ocean is situated primarily in the southern hemisphere. It serves as a vital maritime link between Africa, Asia, and Australia. Unlike the Atlantic and Pacific, which stretch from pole to pole, the Indian Ocean is largely landlocked to the north by the Asian landmass. This unique geography leads to the seasonal reversal of winds known as the monsoons. In summer, warm air rises over the heated land, drawing in moist air from the ocean. In winter, the pattern reverses. These winds exert a powerful influence on the ocean's surface currents and on the climate of the surrounding continents. Monsoon rains are the lifeblood of agriculture for billions of people. The Indian Ocean is also characterized by high surface temperatures and significant tectonic activity. Several mid-ocean ridges crisscross its floor, marking the boundaries of the tectonic plates that are slowly rearranging the face of the planet. The Southern Ocean is unique among the world's basins because it's not defined by continental boundaries. Instead, it's defined by a continuous circumpolar current, the Antarctic Circumpolar Current, which flows uninterrupted around the continent of Antarctica. This current serves as the great connector of the global ocean system. It allows the waters of the Atlantic, Pacific, and Indian Oceans to mix and exchange properties. The northern boundary of the Southern Ocean is generally defined by this current, or sometimes by a feature called the Antarctic Convergence, where cold Antarctic waters meet warmer waters from the north. The Southern Ocean is a critical site for nutrient upwelling and carbon sequestration. The cold, dense waters formed here sink to create the Antarctic bottom water, which flows along the floor of the global ocean, filling the deepest basins. This region is also incredibly productive biologically, supporting vast populations of krill, seabirds, seals, and whales. The upwelling of nutrient-rich deep water fuels phytoplankton blooms that form the base of the food web. Finally, there's the Arctic Ocean, the smallest, shallowest, and most isolated of the major oceanic divisions. It's centered around the North Pole, almost entirely surrounded by the land masses of Eurasia and North America. Much of its surface is covered by a perennial layer of sea ice, although the extent of this ice fluctuates significantly with the seasons and has been shrinking in recent decades due to warming temperatures. The Arctic Ocean is heavily influenced by the discharge of several large rivers. Rivers like the Ob, the Yenisei, the Lena, and the Mackenzie. These rivers pour massive quantities of fresh water into the ocean, creating a distinctive layer of low salinity surface water. This layering is part of what keeps the Arctic so cold. The fresh surface water is less dense and doesn't mix easily with the warmer, saltier Atlantic water that lies beneath. Despite its small size, the Arctic Ocean plays a disproportionately large role in the global climate system. Its ice reflects solar radiation back into space, helping to keep the planet cool. And the salinity balance it contributes to the North Atlantic influences the formation of deep water, which in turn affects the global conveyor belt of currents. Each of these ocean basins These great divisions of the global sea has its own character, its own role in the planetary system. But what shapes them? What determines their depth, their contours, the mountains and valleys hidden beneath the waves? The answer lies in something happening far below the seafloor, in the slow but relentless movement of the Earth's crust. The physical architecture of the ocean basins is a direct result of the movement and interaction of Earth's lithospheric plates. This process, known as plate tectonics, continuously reshapes the seafloor through two primary mechanisms: the creation of new crust and the destruction of old crust. It's a cycle, endlessly repeating itself, that ensures the ocean floor is not a static basin, but a constantly evolving landscape of mountains, plains, and chasms. At what are called divergent boundaries, tectonic plates pull away from each other. Imagine two enormous rafts of rock, each thousands of kilometers across, slowly drifting apart. The gap between them doesn't remain empty. Molten magma rises from the mantle below, filling the space. As it reaches the cold seawater, it solidifies, forming new oceanic floor. This is how the seafloor grows. Conversely, at convergent boundaries, plates collide. When this happens, one plate is often forced to descend beneath the other, diving down into the mantle. This is the mechanism for destroying old crust, for recycling it back into the Earth's interior. The dynamic cycle of creation and destruction ensures that the seafloor is never truly permanent. It's always in motion, always changing, though at a pace so slow that we can't perceive it in a human lifetime. Mid-ocean ridges represent the world's most extensive mountain systems. They wind for over 65,000 kilometers across the global seafloor. To put that in perspective, that's long enough to wrap around the entire planet more than 1.5 times. These ridges form at those divergent plate boundaries we just discussed. Upwelling magma creates a topographic high, a raised area, through thermal expansion and the accumulation of new basaltic rock. As the plates move apart, the newly formed crust cools and contracts. It gradually sinks as it moves away from the ridge axis, the central line where the plates are pulling apart. This process is known as seafloor spreading. It acts as a conveyor belt, constantly producing fresh oceanic lithosphere and pushing the older crust toward the edges of the ocean basins. If you could somehow stand on the ocean floor at a mid-ocean ridge, you'd be standing on some of the youngest rock on Earth. But where does the old crust go? It reaches its limit at subduction zones, the areas where oceanic crust is recycled back into the Earth's interior. When a dense oceanic plate collides with a less dense continental plate, or with another oceanic plate, it's forced downward into the mantle at a steep angle. This process creates deep ocean trenches, the deepest parts of the seafloor. These trenches serve as the physical manifestation of the subduction boundary, the place where one piece of the Earth's crust is diving beneath another. The friction and intense heat generated during subduction often melt the descending plate. This molten rock doesn't just disappear, it rises, fueling the formation of volcanic island arcs, like the Aleutian Islands stretching across the northern Pacific. Or it creates volcanic mountain ranges on the edges of continents, like the Andes, running along the western coast of South America. These are places where the inner fire of the Earth breaks through to the surface. The linear continuity of mid-ocean ridges is frequently interrupted by fracture zones and transform faults. These features appear as massive, jagged scars running perpendicular to the ridge axis, offsetting its segments. Transform faults occur where two plates slide past one another horizontally. They accommodate the uneven stresses generated by the rotation of plates on a spherical Earth. It's a bit like trying to fit flat puzzle pieces onto the surface of a ball. Something has to give, something has to shift. Beyond the active transform boundary, these scars persist as inactive fracture zones, providing a permanent record of the direction and history of plate motion across the ocean floor. A defining characteristic of oceanic crust is its relative youth compared to the continents. Because the seafloor is constantly being created at ridges and destroyed at subduction zones, the oldest oceanic crust is generally less than 200 million years old. This is a stark contrast to continental crust, which can be several billions of years old. Some rocks in Australia and Canada and Greenland have been dated to over 3 billion years. But the ocean floor, it's an infant by geological standards. The age of the seafloor increases symmetrically with distance from the mid-ocean ridge. The rock directly at the ridge is essentially brand new, cooling from molten magma as we speak. The rock near the edges of the basins, approaching the subduction zones, has had millions of years to accumulate sediment and move across the planetary surface. You can map the age of the ocean floor by measuring these distances, and the patterns that emerge are beautifully symmetrical, like the rings of a tree trunk. The Mariana Trench, located in the western Pacific, hosts a place called the Challenger Deep. It is the most profound depression on the Earth's surface. It reaches a depth of nearly 11,000 meters. Think about that for a moment. If you could take Mount Everest, the tallest mountain on Earth, and drop it into the Challenger Deep, its peak would still be covered by over 2 kilometers of water. The seafloor here is further below sea level than Everest is above it. The extreme pressure at these depths is difficult to comprehend. It's over 1,000 times that of the surface. The total absence of light creates a highly specialized environment, one that seems almost alien compared to the sunlit world we know. The formation of such an extreme depth is the result of the oldest, densest part of the Pacific Plate plunging steeply into the Earth's mantle. It's been sinking for millions of years, creating this gash in the ocean floor. Extending from the base of the continental rises are the abyssal plains, which are some of the flattest and most featureless regions on Earth. Located at depths between 3,000 and 6,000 meters, these vast areas are covered in a thick blanket of fine-grained sediments. These are clays, silts, and the remains of microscopic marine organisms, the shells and skeletons of plankton that have been raining down from the surface for millennia. These sediments gradually fill in the rugged topography of the underlying volcanic crust, resulting in a level surface that can extend for hundreds of kilometers. Abyssal plains cover more than half of the Earth's surface. They form the vast basement of the global ocean, a dark, flat expanse where very little changes from one year to the next. The transition between the shallow continental shelves and the deep abyssal plains is often carved by submarine canyons. These are steep-sided, V-shaped valleys, frequently as large and dramatic as the Grand Canyon on land. Many are located directly offshore from major river systems. They were originally formed by the erosive force of what are called turbidity currents, fast-moving, sediment-laden underwater avalanches. When sediments accumulate on the continental shelf or slope, they can become unstable. A trigger, perhaps an earthquake or a storm, can send them cascading down the slope in a dense, churning cloud. These currents are powerful enough to carve deep valleys into the sea floor. Submarine canyons serve as vital conduits, transporting terrestrial sediments and nutrients from the coastal margins down into the deep sea basins, effectively bridging the terrestrial and deep marine worlds. The global ocean is characterized by its immense vertical scale. The average depth is approximately 3,700 to 3,800 meters. To put this in perspective, the average elevation of the world's land masses is only about 840 meters above sea level. This disparity means that the volume of habitable space within the ocean is far greater than that on land. When we think of the biosphere, we often picture forests and grasslands and cities, but the vast majority of the living space on Earth is underwater. It's a three-dimensional realm extending from the surface down into the abyss. The vast majority of the ocean floor exists as a dark, cold abyss. The deep-sea basins and trenches provide a much larger physical footprint than the continental shelf areas that border the land. Those shelves, where the ocean is shallow and sunlight reaches the bottom, are a tiny fraction of the total. Most of the ocean is deep, dark, and cold. One of the most significant physical constraints of the marine environment is hydrostatic pressure, which increases linearly with depth. For every 10 meters of descent, the weight of the water column above adds approximately 1 atmosphere of pressure. While organisms at the surface experience the standard 1 atmosphere of pressure from the air, a creature at the average ocean depth lives under nearly 400 atmospheres. In the deepest reaches of the Mariana Trench, the pressure exceeds 1,000 atmospheres. That's roughly equivalent to the weight of an elephant balanced on a human thumb. Any life existing there requires specialized cellular and structural adaptations. Proteins have to be modified. Cell membranes need to remain flexible despite the crushing force. It's a world where the ordinary rules don't apply. Solar radiation is the primary energy source for marine life, but its reach is limited by the optical properties of water. Sunlight is absorbed and scattered as it enters the ocean. Only the uppermost layer receives enough light to support photosynthesis. This layer is known as the euphotic zone, and it typically extends to a depth of about 200 meters in clear, open ocean waters. In coastal areas, where sediment and plankton cloud the water, it may extend only a few tens of meters. This thin skin of the ocean is the biological powerhouse of the planet. In the euphotic zone, phytoplankton, microscopic plants drifting in the current, use sunlight to convert carbon dioxide and water into organic matter. They produce oxygen as a byproduct. In fact, phytoplankton are responsible for roughly half of the oxygen in Earth's atmosphere. Every second breath you take comes from the ocean. These tiny organisms form the foundation of nearly all marine food webs, providing the energy that sustains everything from zooplankton to fish to whales. Beyond the euphotic zone, the ocean transitions into the dysphotic zone, sometimes called the twilight zone. Here, light is insufficient for photosynthesis, but enough for some organisms to see. It's a realm of faint blue-green illumination where visibility exists but is dim and murky. Many organisms in this zone have adapted to low-light conditions, developing large eyes or light-sensing organs. By a depth of 1,000 meters, the ocean enters the aphotic zone, a realm of perpetual darkness. Here, the only light produced is bioluminescence, chemically generated light from specialized organisms. Some fish and squid and jellyfish have evolved the ability to create their own light, using it to attract prey, to communicate, or to confuse predators. In this vast interior, the lack of solar energy means that deep-sea ecosystems must rely on what's called marine snow, a continuous drizzle of organic debris falling from the surface. Surface ocean temperatures are highly variable and are primarily determined by latitude and the amount of solar insolation received. In the equatorial and tropical regions, surface waters can exceed 25 to 30 degrees Celsius. These warm, buoyant layers sit atop the water column, creating a stable environment that resists mixing with the colder water below. Conversely, near the North and South Poles, surface temperatures drop to the freezing point of seawater, 0 degrees Celsius, around minus 1.9 degrees Celsius. These surface temperature gradients drive the atmospheric wind patterns and the major surface currents that circulate water across the globe. In stark contrast to the variable surface, the deep ocean is characterized by extreme thermal stability. Below the thermocline, that transition layer we discussed earlier, where temperature drops rapidly, the vast majority of the ocean's volume is consistently cold. Typically, it ranges between 0 and 3 degrees Celsius. This remains true even in the tropics. Beneath the sun-warmed surface, several kilometers of frigid water sit in darkness. This deep, cold water originated at the poles, where it became dense enough to sink and flow toward the equator, filling the global ocean basins with a massive, slow-moving reservoir of near-freezing water. It's a hidden world, a cold, dark realm that most people never think about, but that contains the majority of the ocean's volume. Ocean currents function as a massive, horizontal circulatory system for the planet, moving immense volumes of water across thousands of miles. This motion is not merely the displacement of liquid, it's the primary mechanism for redistributing solar energy from the tropics toward the poles, ensuring that the Earth's climate remains balanced. By transporting heat as well as essential dissolved nutrients and gases like oxygen and carbon dioxide, these currents dictate the productivity of marine ecosystems and the habitability of coastal regions. The primary force behind surface currents is the friction of global wind patterns against the water's surface. The trade winds near the equator, the westerlies in the mid-latitudes, the polar easterlies, all of these push against the ocean, setting it in motion. This interaction, combined with the Earth's rotation, causes surface waters to organize into massive, nearly circular flow patterns known as gyres. These gyres dominate the major ocean basins. They act as large-scale recycling systems that trap water within their centers. Because the land masses of the continents act as barriers, the water is forced to turn as it reaches the edges of the basins, completing the circular path. Due to the Coriolis effect, the deflection of moving objects caused by the Earth's rotation, the direction of these gyres depends on the hemisphere. In the northern hemisphere, the subtropical gyres rotate in a clockwise direction. In the southern hemisphere, the rotation is reversed, flowing counterclockwise. This symmetry is a fundamental consequence of the Earth's spin. It determines how heat is ferried away from the equator on either side of the globe. The most intense segments of these gyres are found on the western side of ocean basins. These are called western boundary currents. Examples include the Gulf Stream in the North Atlantic and the Kuroshio Current off the coast of Japan. These currents are narrow, deep, and extremely fast. They act as express lanes, transporting warm tropical water toward higher latitudes. The heat released by these currents significantly warms the atmosphere of northern regions. The Gulf Stream, for instance, is responsible for the relatively mild winters experienced in Western Europe. Without it, places like Ireland and England would have climates much more similar to Labrador in Canada, which sits at the same latitude. Conversely, eastern boundary currents flow along the eastern side of ocean basins, moving from the poles back toward the equator. These currents, such as the Peru Current, also called the Humboldt Current off South America, or the Benguela Current off Africa, are generally broader, shallower, and much cooler than their western counterparts. Because they carry nutrient-rich, cold water, these regions are often associated with productive fishing grounds. They are also associated with coastal fog, as the cold water chills the air above it, causing moisture to condense. In the equatorial regions, the trade winds drive broad westward flowing currents known as the North and South Equatorial Currents. These massive flows of water push sun-warmed surface layers across the Atlantic, Pacific, and Indian Oceans. As this water moves westward, it gradually gains more heat from the sun. It piles up against the western edges of the basins, creating a slight elevation in sea level. This elevation helps fuel the powerful western boundary currents, providing a pressure gradient that accelerates the flow. To balance this westward accumulation of water, narrow eastward flowing countercurrents exist between the major equatorial flows. These equatorial countercurrents flow downhill, so to speak, against the prevailing winds, returning some of the accumulated water back toward the east. Though narrower and less powerful than the main equatorial currents, they're essential for the overall mass balance of the ocean surface. They also influence the distribution of marine larvae and heat in the tropics. The Southern Ocean features a unique current that has no continental barriers to stop it, the Antarctic Circumpolar Current. This current flows continuously eastward around the entire continent of Antarctica. It is the most powerful current on Earth by volume. It acts as the great connector, allowing water and heat to be exchanged between the Atlantic, Pacific, and Indian Oceans. This circulation effectively isolates the Antarctic continent from warmer northern waters, maintaining the massive ice sheets that cover the land. In the northern Indian Ocean, the geography of the surrounding landmasses creates a unique seasonal phenomenon. Unlike other ocean basins where currents are relatively steady throughout the year, the currents here reverse their direction twice a year in response to the monsoons. During the summer, the winds blow from the southwest, driving the water eastward. In the winter, the winds shift to the northeast, reversing the flow. This reversal has a profound impact on local marine productivity and regional weather patterns. When the currents shift, they bring different water masses with different nutrient levels, affecting everything from fish populations to rainfall patterns across South Asia. While the ocean moves at all depths, wind-driven circulation is the most vigorous and rapid part of the global system. This activity is largely confined to the upper few hundred meters of the water column, the layer in direct contact with the atmosphere. Although it involves only a small fraction of the ocean's total volume, this wind-driven layer is responsible for the majority of the heat transport that regulates our daily weather and seasonal climates. It's the part of the ocean that responds most quickly to changes in atmospheric conditions. But there's another type of circulation, one that operates on a much slower timescale. Thermohaline circulation represents the deep-seated, slow-moving pulse of the global ocean. It functions independently of the rapid, wind-driven surface currents. This internal engine is powered by gradients in density, which, as we've discussed, are determined by the interplay between temperature and salinity. While surface currents may move at speeds of several kilometers per hour, the deep thermohaline flow typically progresses at a rate of only a few centimeters per second. You could walk faster than this water moves, but despite this slow pace, it involves the movement of massive volumes of water, far exceeding the flow of all the world's rivers combined. This interconnected system is frequently visualized as a global conveyor belt that facilitates the continuous exchange of water between the surface and the abyss. In this model, warm surface waters move toward the poles. As they travel north or south, they lose heat to the atmosphere. The air above the ocean is colder than the water, so heat radiates away. The water becomes denser as it cools. In some places, it becomes dense enough to sink, plunging thousands of meters to the seafloor. These waters then travel through the deep basins of the Atlantic, Indian, and Pacific Oceans, following the contours of the ocean floor. Eventually, after centuries or even a millennium, they warm slightly and rise back to the surface to complete the circuit. This planetary scale loop is essential for maintaining the chemical and thermal equilibrium of the entire Earth system. It ensures that no part of the ocean remains stagnant or isolated. The formation of the world's densest water occurs in just a few specific high-latitude regions. The Weddell Sea off Antarctica is one. The Labrador and Greenland seas in the North Atlantic are others. In these areas, the combination of extreme cold and the exclusion of salt during ice formation creates water masses of such high density that they plummet thousands of meters to the seafloor. Once submerged, these deep water masses flow along the bottom of the ocean. A single parcel of water may take anywhere from several hundred to over 1,000 years to complete a full transit from its sinking point back to the surface. It's a journey almost beyond comprehension, a slow drift through the dark and cold. The oldest water in the global circulation, measured by the time elapsed since it was last in contact with the atmosphere, is located in the deep North Pacific. By the time deep water reaches this region, it has traveled the furthest distance along the conveyor belt. It has slowly accumulated nutrients and dissolved inorganic carbon from the decomposition of organic matter falling from above. Marine snow, the bodies of dead plankton, fish waste, all of this rains down from the surface, decomposing as it sinks. The bacteria that break it down consume oxygen and release carbon dioxide and nutrients. Because this water has been sequestered from the surface for roughly a millennium, it's depleted of dissolved oxygen compared to younger deep waters found in the Atlantic. It marks the final stage of the deep-sea journey before the water begins its gradual ascent, eventually upwelling in places where deep water is brought back to the surface. Part 2. And what brings that deep water back to the surface? What completes the cycle? The answer is upwelling, the process by which these deep, cool waters are drawn back toward the surface. This typically occurs along the western coasts of continents or along the equator, where prevailing winds and the Earth's rotation push surface waters away from the coast or away from the center. Picture the wind blowing parallel to a coastline, pushing the surface water offshore. As that surface water is displaced, it has to be replaced by something. And what replaces it is water from below, nutrient-rich water that has been sitting in the depths, accumulating nutrients from the decomposition of organic matter. These nutrients, such as nitrates and phosphates, act as fertilizer for phytoplankton. When they reach the sunlit surface, they trigger bursts of biological productivity. This is why upwelling zones support some of the most abundant fisheries and complex marine food webs on the planet. Off the coast of Peru, off the coast of California, along the coast of Namibia, these are places where cold, nutrient-laden water rises from the deep, and life explodes in response. Conversely, downwelling occurs when surface waters are forced downward. This can happen due to the convergence of surface currents, where two currents meet and the water has nowhere to go but down. It can also happen when surface water cools and becomes denser, or when evaporation increases salinity, making the water heavy enough to sink. While upwelling brings nutrients up, downwelling acts as a vital delivery system for the deep sea. It carries dissolved oxygen from the surface down to the organisms living in the dark abyss. Without this constant replenishment of oxygen through downwelling, the deep ocean would eventually become anoxic, depleted of oxygen, making it impossible for larger multicellular life to survive in the deep basins. This global circulation system is a fundamental regulator of the Earth's climate. It acts as a massive heat and carbon transport mechanism. By moving warm water toward the poles and cold water toward the equator, it prevents extreme temperature gradients that would otherwise make many parts of the planet uninhabitable. Furthermore, by carrying dissolved carbon dioxide into the deep ocean, where it can be stored for centuries, the circulation effectively buffers the atmosphere against rapid increases in greenhouse gas concentrations. Though this capacity is finite, it has been buying us time. The stability of the thermohaline circulation is highly sensitive to changes in fresh water input. Large additions of fresh water from the melting of polar ice sheets, increased rainfall, or river runoff can lower the salinity and therefore the density of surface waters in those critical sinking regions we talked about. If the surface water becomes too buoyant, too light, it may fail to sink. and if it fails to sink, the conveyor belt could stall. Such a disruption would significantly alter the transport of heat, leading to profound shifts in regional weather patterns, particularly in the North Atlantic region. Scientific observations indicate that parts of the thermohaline circulation, specifically the Atlantic Meridional Overturning Circulation, often abbreviated as AMOC, have shown signs of slowing in recent decades. This weakening is attributed to the warming of the ocean surface and the increased melting of the Greenland ice sheet. While the exact threshold for a total collapse of this system remains a subject of intense research and uncertainty, even a partial slowing of the circulation has the potential to shift tropical rainfall belts, accelerate sea level rise along certain coastlines, and alter the ocean's ability to absorb heat and carbon. These are changes with far-reaching consequences, rippling through both natural and human systems. The ocean serves as a vast reservoir for atmospheric gases. The concentrations of dissolved oxygen, carbon dioxide, and nitrogen are determined by a complex interplay of physical and biological factors. Nitrogen is the most abundant dissolved gas, but it remains largely inert for most marine organisms. It's there, dissolved in the water, but very few creatures can actually use it directly. In contrast, oxygen and carbon dioxide are highly dynamic. Their levels are constantly being shifted by the metabolic activities of life. Photosynthesis produces oxygen. Respiration consumes it. Solubility is further influenced by environmental conditions. For instance, increased hydrostatic pressure at greater depths can keep gases in solution, while biological processes act as the primary sources and sinks for these essential elements. The capacity of seawater to hold dissolved oxygen is inversely related to its temperature. Colder water molecules are less energetic. They move more slowly, allowing them to retain gas molecules more effectively than warmer, more active water. Consequently, the frigid surface waters near the poles are typically much richer in oxygen than the warm waters of the tropics. This physical law has profound implications for the distribution of marine species. High-latitude ecosystems can support large, highly active organisms with high metabolic demands: whales, seals, large fish. Warming ocean temperatures, on the other hand, can lead to a decrease in oxygen solubility, potentially stressing marine life and shifting their geographic ranges. As the ocean warms, some species are moving poleward, following the cold water. Within the water column, specific regions known as oxygen minimum zones occur, typically at depths between 200 and 1,000 meters. These zones form because of a biological bottleneck. While the surface is replenished by the atmosphere and by photosynthesis, the intermediate depths are sites of intense microbial activity. As organic matter, dead plankton, fecal pellets, sinks from the sunlit surface, it's decomposed by bacteria. This process of aerobic respiration consumes dissolved oxygen at a rate faster than it can be replaced by mixing or circulation. In these areas, oxygen levels can drop to near zero, creating a challenging environment. Only specialized organisms adapted to low oxygen conditions can inhabit these zones. Some have evolved the ability to switch to anaerobic metabolism. Others have developed ways to store oxygen internally or to extract it with extreme efficiency. The ocean serves as a vast, multidimensional habitat that supports an immense variety of biological life, spanning several orders of magnitude in size. This diversity ranges from microscopic single-celled organisms to the blue whale, the largest animal known to have ever existed. A blue whale can reach lengths of over 30 meters and weigh as much as 200 tons. Because the marine environment is interconnected and three-dimensional, life has colonized every available niche, from the sun-drenched surface to the crushing pressures of the deepest trenches. The complexity of these ecosystems is driven by the physical properties of the water itself, which provides buoyancy, a medium for chemical signaling, and a relatively stable thermal environment. At the very foundation of the marine food web are phytoplankton, a diverse group of microscopic photosynthetic organisms that inhabit the euphotic zone. These drifters, which include diatoms and dinoflagellates, function similarly to terrestrial plants by converting solar energy and carbon dioxide into organic matter. Despite their size, their collective impact is monumental. They produce approximately half of the world's atmospheric oxygen, half, and they serve as the primary source of nutrition for the entire oceanic hierarchy. Their growth is strictly governed by the availability of sunlight and dissolved nutrients, making them highly sensitive to changes in ocean temperature and circulation. Zooplankton represent the second tier of the marine food web, consisting of small animals and animal-like protists that drift with the currents. This group includes a wide array of organisms, from tiny crustaceans like copepods and krill to the larval stages of fish and invertebrates. Zooplankton act as a critical energy bridge. They consume phytoplankton, converting that plant matter into animal tissue, and then they're consumed by larger predators. Many zooplankton species participate in what's called the diel vertical migration, the largest synchronized migration on Earth. Every night, as darkness falls, billions upon billions of these small creatures rise from the deep, dark water to feed near the surface under the cover of darkness. As dawn approaches, they descend again, spending the daylight hours at depth to avoid predators that hunt by sight. In the open ocean, the pelagic zone, evolution has favored organisms capable of sustained, high-speed movement through a vast, three-dimensional space. Apex predators, such as tuna, billfish, and various shark species, possess streamlined, fusiform bodies that minimize drag. They have specialized muscular systems designed for endurance. Many of these species are what's called ram ventilators, meaning they must swim constantly to push oxygenated water over their gills. If they stop swimming, they can't breathe. Unlike coastal species that can hide in structures, in reefs, in kelp forests, these open ocean animals rely on speed, on camouflage, often in the form of countershading where they're dark on top and light on the bottom, and on highly developed sensory systems to find prey and navigate the trackless expanse. Nearer to the coast, biological productivity is concentrated in complex ecosystems like coral reefs. These structures are built by colonies of tiny conidarians called coral polyps. Each polyp is a small, soft-bodied animal related to jellyfish and sea anemones. They extract calcium carbonate from seawater to construct rigid skeletons. Over thousands of years, these skeletons accumulate to form massive three-dimensional structures. Although coral reefs cover less than 1% of the ocean floor, they're among the most biodiverse habitats on the planet. They provide shelter, breeding grounds, and hunting territories for an estimated 25% of all marine species. Fish, mollusks, crustaceans, sponges, sea stars. The diversity is staggering. In cooler, nutrient-rich coastal waters, kelp forests serve as the dominant ecosystem. These are formed by large brown macroalgae, essentially giant seaweeds, that attach to the seafloor with specialized structures called holdfasts. They grow toward the surface using gas-filled bladders known as pneumatocysts, which provide buoyancy. In ideal conditions, kelp can grow at extraordinary rates, up to 60 centimeters per day. That's among the fastest growth rates of any organism on Earth. These plants create dense underwater canopies that attenuate wave energy, calming the waters beneath them. They provide a complex habitat for fish, invertebrates, and sea otters. Kelp forests are vital for carbon sequestration, absorbing carbon dioxide from the water, and they serve as protective nurseries for many commercially important fish species. Seagrass meadows represent another critical coastal habitat. These are composed of true flowering plants, not algae, that have adapted to a fully submerged existence. They possess extensive root and rhizome systems that anchor them into the sediment, which helps stabilize the seafloor and prevent erosion. Seagrasses are highly efficient at filtering particles from the water column, improving water clarity. And they're incredibly effective at storing what's called blue carbon, carbon captured by ocean ecosystems, in their roots and in the surrounding soil. They provide essential grazing grounds for large herbivores like sea turtles and dugongs, as well as a sanctuary for juvenile fish and crustaceans. Along tropical and subtropical coastlines, mangrove forests bridge the gap between land and sea. These specialized trees have evolved unique physiological adaptations to thrive in saline, oxygen-poor sediments where most other plants would perish. Their most striking feature is their complex aerial root systems. They have prop roots, roots that arch out from the trunk and plunge into the mud like flying buttresses. They have pneumatophores, roots that stick up out of the sediment like snorkels, allowing the tree to breathe even when the tide is high. These roots create a tangled underwater labyrinth. They protect coastlines from storm surges, dissipating wave energy before it can reach the land. And they provide a nutrient-rich nursery for a vast array of marine life: fish, crabs, shrimp, oysters. The vastness of the ocean requires many marine species to undertake massive migrations to satisfy their life cycle requirements. Whales, seals, sea turtles, these animals often travel thousands of miles between high-latitude feeding grounds, where seasonal blooms provide abundant food, and lower-latitude breeding grounds, where warmer waters are more suitable for raising young. These migrations are often precisely timed with seasonal shifts in productivity, and they rely on sophisticated navigational abilities. Some species can detect the Earth's magnetic field, using it like a compass. Others follow chemical cues in the water or navigate by celestial patterns, by the position of the sun or the stars. Marine mammals, such as cetaceans, whales, dolphins, porpoises, and pinnipeds, seals, sea lions, walruses, have maintained their ancestral need to breathe atmospheric air while becoming masterfully adapted to the deep. To facilitate extended dives, these animals have evolved high concentrations of myoglobin in their muscles. Myoglobin is a protein that stores oxygen, similar to hemoglobin in the blood. They also have the ability to collapse their lungs, which helps them avoid the effects of high pressure and prevents nitrogen from dissolving into their tissues and causing decompression sickness, the bends. They utilize what's called a diving reflex that slows the heart rate and redirects blood flow exclusively to the brain and heart. These adaptations allow species like the sperm whale to hunt in the lightless depths for over an hour before returning to the surface to replenish their oxygen supply. The deep sea begins where the sun's influence fades, typically defined as the vast volume of water extending from a depth of 200 meters down to the sea floor. This environment is defined by three extreme physical constraints: perpetual darkness, near freezing temperatures, and immense hydrostatic pressure that increases by 1 atmosphere for every 10 meters of depth. Because the primary production of food via photosynthesis is impossible in this realm, the deep sea is what's called an oligotrophic environment, one where energy is a precious and limited resource. Survival here requires specialized physiological and behavioral strategies to navigate a world that is fundamentally different from the sunlit surface. To survive in a habitat where food arrives only fitfully as organic marine snow from above, many deep-sea organisms have evolved exceptionally slow metabolic rates. By reducing their energy expenditure, these animals can endure long periods of fasting. This physiological conservation often manifests in slow movement, minimal muscle mass, and tissues with high water content. This is life in the slow lane. It allows deep-sea creatures to thrive on a fraction of the calories required by their shallow water counterparts, turning what would be a starvation environment for most animals into a stable, albeit sparse, home. Bioluminescence, the biological production of light, is the primary source of illumination in the deep ocean. It's estimated to occur in 75 to 90% of deep-sea life. In a realm where solar photons cannot penetrate, organisms have evolved the ability to generate their own living light. This phenomenon is not merely a curiosity, it's a central survival mechanism serving as a substitute for sunlight in the largest habitat on Earth. Because water is most transparent to blue and green wavelengths, the majority of bioluminescence in the deep sea appears in these colors, allowing the signals to travel as far as possible through the dark water column. The mechanism behind this light is a specialized biochemical reaction occurring within the organism's cells or inside complex structures called photophores, essentially light organs. The process typically involves a light-emitting molecule known as a luciferin and a catalyst enzyme called luciferase. When these components interact in the presence of oxygen, energy is released in the form of cold light. The functional roles of bioluminescence are incredibly diverse. They're often categorized into defense, offense, and communication. Some predators, like the anglerfish, use a glowing lure to attract curious prey toward their jaws. The anglerfish has a modified dorsal fin spine that extends out in front of its face like a fishing rod with a glowing bulb at the tip. Small fish or shrimp, drawn to what looks like a tasty morsel, swim closer and find themselves face to face with a mouth full of teeth. Others use counter-illumination, a form of camouflage where light organs on their underside match the faint light filtering down from above. This erases their silhouette from predators lurking below. It's a clever trick. If you're looking up from the depths, the animal blends in with the dim glow from the surface, becoming nearly invisible. Additionally, flashes of light can be used as burglar alarms. If a small organism is being attacked, it can emit a bright flash or cloud of bioluminescent fluid. This reveals the predator to even larger hunters nearby, creating a distraction that might allow the prey to escape. And bioluminescence can be used as a means of identifying and attracting mates in the vast, lightless void. Specific patterns and colors serve as species-specific signals, like a secret code understood only by others of your kind. In response to these faint biological signals, many deep-sea fish have evolved highly specialized visual systems. Their eyes are often disproportionately large or tubular, designed to maximize light-gathering capabilities. These eyes frequently contain high densities of rod cells, the photoreceptors responsible for detecting low light levels. They lack cone cells, the ones used for color vision in bright light. Some species have even evolved yellow lenses that act as filters to help distinguish between the natural blue bioluminescence of prey and the camouflaging light of others. It's a complex game of visual detection and deception, where the ability to see or to hide in the faint glow can mean the difference between life and death. Bioluminescence is not always produced by the animal itself. Many deep-sea creatures host colonies of naturally luminous bacteria within specialized light organs. In this symbiotic relationship, the animal provides the bacteria with a steady supply of nutrients and a protected environment. In return, the bacteria provide a reliable source of light that the animal can control using shutters or lenses, much like adjusting a lantern. This partnership is so refined that the host's nervous system can often regulate the intensity and timing of the bacterial glow, allowing the animal to use the light for its own survival needs, whether for hunting, signaling, or camouflage. Beyond its role as a visual signal, bioluminescence appears to have deep-seated physiological benefits for the bacteria themselves. Laboratory experiments conducted under high-pressure conditions have revealed that bioluminescent strains of deep-sea bacteria are more resilient to oxidative stress than their non-luminous counterparts. When subjected to the crushing pressures of the deep, cells can produce reactive oxygen species that damage DNA and proteins. The bioluminescent pathway seems to mitigate this damage, suggesting that the light-producing reaction evolved not just for visibility, but as a vital cellular defense mechanism. This research indicates that in certain deep-sea bacteria, the bioluminescent system functions as a sophisticated antioxidant mechanism. By channeling excess energy and oxygen into the production of light, the bacteria can neutralize potentially harmful molecules that accumulate under high hydrostatic pressure. This discovery provides a new perspective on the evolution of bioluminescence. It suggests that the ability to produce light may have originally appeared as a metabolic byproduct or a stress response strategy before being co-opted for the myriad of ecological and communicative roles it plays in the ocean today. It's a reminder that evolution is opportunistic, taking whatever tools are available and repurposing them for new functions. In the profound darkness of the deep ocean floor where sunlight cannot reach, life is sustained through a process called chemosynthesis. This metabolic pathway is utilized by specialized microbes that extract energy from the chemical bonds of inorganic molecules. Part 3. Inorganic molecules, such as hydrogen sulfide and methane, found in fluids emerging from the Earth's crust. Unlike the surface world, which is solar-powered, these hydrothermal vent communities are entirely decoupled from the sun. They are the only ecosystems on Earth driven by the internal geochemical energy of the planet. It's life powered not by light, but by the heat and chemistry of the Earth's interior. Among the most dramatic features of these environments are black smokers, tall chimney-like structures formed at seafloor spreading centers. These vents emit superheated, acidic fluids that can reach temperatures exceeding 350 degrees Celsius. That's hot enough to melt lead. As this mineral-laden fluid meets the near-freezing alkaline seawater, a reaction occurs. Dissolved metals, such as iron and manganese, react with sulfur to precipitate as dark, smoke-like particles. It looks like a plume of black smoke rising from a chimney, hence the name. These particles settle and build massive mineral chimneys over time, chimneys that serve as the physical and chemical foundation for the surrounding biological community. The animals that inhabit these vents have evolved intimate, symbiotic relationships with chemosynthetic bacteria. Giant tube worms are perhaps the most famous example. These creatures can grow to lengths of over 2 meters, and remarkably, they lack a mouth or digestive tract. Instead, they possess a specialized organ called a trophosome, filled with billions of symbiotic microbes. The worm's blood transports oxygen and hydrogen sulfide from the vent fluid to the bacteria. In exchange, the bacteria synthesize organic molecules that provide the worm with 100% of its nutrition. It's a complete partnership. Similar relationships exist in vent clams and mussels, allowing these larger organisms to flourish in what is, by most standards, a chemically toxic environment. In contrast to the violent, high-temperature discharge of hydrothermal vents, cold seeps occur where fluids rich in methane or petroleum slowly migrate through the seafloor. These seeps are often found at continental margins, the edges where continents meet the deep ocean. They're much cooler and more stable than vents. The methane escaping from the sediment fuels consortia of bacteria and archaea, which in turn support vast beds of mussels and tube worms. Because these fluid flows can persist for centuries, far longer than the typical lifespan of a hydrothermal vent, cold seep ecosystems often develop greater complexity and higher longevity. A unique biological event in the deep sea is what's called a whale fall. This occurs when the carcass of a large cetacean sinks to the abyssal floor. This massive influx of organic matter potentially dozens of tons of flesh, bone, and blubber, creates a localized oasis in the otherwise food-poor deep sea. The ecosystem that develops progresses through distinct ecological stages. Initially, mobile scavengers like hagfish and sharks arrive, consuming the soft tissue. This phase can last months. Later, opportunistic invertebrates colonize the bones and surrounding sediment. In the final stage, which can last for years or even decades, anaerobic bacteria break down the lipids stored inside the bones. This releases hydrogen sulfide, and chemosynthetic organisms settle on the skeleton, effectively turning the whale's remains into a temporary hydrothermal-style ecosystem. It's a gift from the surface, sustaining life in the deep long after the whale's death. The vast majority of the deep sea floor consists of extensive soft sediments composed of fine silts, clays, and the remains of microscopic plankton. This material is sometimes called abyssal ooze, and it's populated by a diverse community of infauna, animals that live within the sediment. These include polychaete worms, small crustaceans, and mollusks. Surface-dwelling echinoderms, such as sea cucumbers and brittle stars, move slowly across these plains, acting as the primary recyclers of organic debris. They vacuum up the sediment, extracting whatever nutrients they can. This habitat represents the largest single ecosystem on the planet. It's characterized by a high diversity of specialized species, despite the apparent uniformity of the landscape. If you were to collect samples from different abyssal plains around the world, you'd find that each one hosts its own distinct community of species, many of them found nowhere else. Because the deep sea is generally a realm of extreme physical stability, where currents are weak, temperatures vary by less than a degree, and the environment has remained largely unchanged for millions of years. Many deep-sea organisms have evolved extremely fragile bodies. Without the need to withstand the turbulent energy of surface waves or the pursuit of fast predators, these animals often possess gelatinous tissues and delicate skeletal structures. This specialization makes them highly efficient in their native habitat, requiring minimal energy to maintain their bodies. But it also makes them exceptionally vulnerable to any external disturbances, such as deep-sea mining or shifts in ocean chemistry. They lack the resilience required to survive rapid environmental change. Sound is the primary sensory medium of the underwater world. Water is an exceptionally efficient conductor of acoustic energy compared to air. Because water is denser and less compressible than air, sound waves travel approximately 4.5 times faster in the ocean, roughly 1,500 meters per second. And while light is absorbed within the first few hundred meters, sound can propagate across thousands of kilometers with minimal loss of intensity. This physical property has led to the evolution of sophisticated acoustic adaptations in marine life. Sound is used for echolocation, for identifying mates, for maintaining social structures, and for navigating through an environment where vision is often obscured by darkness or turbidity. A unique acoustic phenomenon known as the SOFAR channel exists in the deep ocean. SOFAR stands for sound fixing and ranging. This channel is typically centered at a depth of about 1,000 meters. It's created by the competing effects of temperature and pressure on the speed of sound. Near the surface, water is warmer and sound travels faster. As you descend and the water cools, sound slows down. But as you go deeper still, pressure increases, and that pressure speeds sound back up. At the SOFAR channel, these two effects balance out, and the speed of sound reaches a minimum. Sound waves that attempt to exit the layer, either upward or downward, are refracted back into it. This effectively traps the acoustic energy in a horizontal waveguide, preventing it from being absorbed by the seafloor or scattered by the surface. Low-frequency noises can travel halfway around the planet while retaining enough clarity to be detected by specialized biological or mechanical receivers. Baleen whales, such as blue whales and fin whales, are the masters of long-distance acoustic communication. They produce low-frequency vocalizations that are perfectly suited for the SOFAR channel. These sounds, which can be as loud as a jet engine at the source, exist at frequencies below 100 Hz. These are wavelengths that are far too long to be easily absorbed by the water. Under the right oceanographic conditions, these songs can propagate across entire ocean basins. This allows individuals separated by thousands of miles to remain in contact, sharing information about feeding grounds or breeding availability in a way that would be impossible for any terrestrial animal. It's as if the entire ocean becomes a medium for conversation. The reliance on sound makes marine organisms particularly vulnerable to changes in their acoustic environment. The underwater soundscape is naturally a mix of sounds: breaking waves, rain pattering on the surface, tectonic activity, the crackling of snapping shrimp, the grunts and whistles of countless species, what are sometimes called biological choruses. But increasingly, there's anthropogenic noise. Human activities, including commercial shipping, seismic surveys for oil and gas, and military sonar, have significantly raised the background noise levels in the ocean. This acoustic smog can mask the vital signals used by marine life, leading to increased stress, the disruption of feeding and mating behaviors, and in extreme cases, physical injury or disorientation that can result in mass strandings. Whales have been found beached after exposure to intense sonar, their inner ears damaged, their ability to navigate destroyed. The productivity of the marine world is fundamentally governed by the availability of dissolved inorganic nutrients. These are primarily nitrates, phosphates, and silicates. These chemical compounds serve as the essential building blocks for phytoplankton, the microscopic primary producers of the ocean. Nitrates and phosphates are critical for the synthesis of proteins and DNA, the fundamental machinery of life. Silicates are specifically required by certain groups, such as diatoms, to construct their glass-like cell walls. Because these nutrients are typically found in much lower concentrations than the salts in seawater, they act as the limiting factors that determine the carrying capacity of a given marine ecosystem. Where nutrients are abundant, life blooms. Where they're scarce, the ocean can be almost empty. In a typical ocean profile, nutrients are characterized by what's called a depletion-accumulation cycle. In the sunlit euphotic zone, phytoplankton rapidly consume these chemicals as they grow and reproduce. During a bloom, they can strip the surface waters of nutrients to near zero levels in a matter of weeks. When these organisms die or are eaten, their organic remains sink into the darker, deeper layers of the water column. There, specialized bacteria decompose the material, a process that mineralizes organic matter and releases the nutrients back into the water in their inorganic form. Consequently, the deep ocean acts as a massive nutrient bank, sequestering the chemicals needed for life far below the reach of the sunlight required to use them. It's a cruel irony in a way. Nutrients are abundant in the dark, where they can't be used, and scarce in the light, where they're desperately needed. The return of these deep-seated nutrients to the surface occurs through the physical process of upwelling. This happens most intensely along the western edges of continents and along the equator, where wind-driven currents pull surface waters away, allowing the cold, nutrient-rich deep water to rise and replace it. These upwelling zones are the most biologically fertile regions of the global ocean. Although they occupy a small fraction of the ocean's surface area, they support the majority of the world's commercial fisheries. They provide the energy required for massive populations of seabirds and marine mammals. It's where life congregates, drawn by the abundance of food. While nitrogen and phosphorus are the primary nutrients, the growth of phytoplankton in vast areas of the open ocean is limited by the scarcity of iron. These regions are known as high nitrate, low chlorophyll regions, or HNLC regions. They have plenty of the major nutrients, but they're missing iron, a trace element necessary for the biochemical machinery of photosynthesis and nitrogen fixation. Because iron is poorly soluble in seawater and primarily enters the ocean via wind-blown continental dust or volcanic ash, regions far from land often lack the necessary amounts to sustain large blooms. This iron hypothesis explains why some parts of the ocean remain biological deserts, despite having an abundance of other major nutrients. It's like having all the ingredients for bread except yeast. Nothing rises. Energy is transferred from the surface to the abyss through marine snow, that continuous rain of organic detritus we mentioned earlier. This material consists of dead or dying plankton, protist cells, fecal pellets from zooplankton, and mucus-based structures. As these particles sink, they often clump together, aggregating into larger and larger masses, becoming heavy enough to descend through the water column. Marine snow provides the primary source of food for the organisms living in the aphotic zone and the deep sea floor. It acts as a vital tether between the sunlit world above and the dark world below. This downward movement of organic matter is the mechanical core of what's called the biological pump, a process that effectively pumps carbon from the atmosphere and surface ocean into the deep interior. By converting dissolved carbon dioxide into organic tissue through photosynthesis and then transporting that tissue to depth via sinking, the biological pump sequesters carbon away from the atmosphere for centuries or even millennia. This system is a critical component of the Earth's carbon cycle, as it helps regulate global temperatures by maintaining a lower concentration of atmospheric carbon dioxide than would exist in a sterile ocean. Without the biological pump, without this rain of dead organisms carrying carbon into the deep, atmospheric carbon dioxide levels would be significantly higher. Once carbon enters the ocean, it doesn't remain solely as dissolved gas. It participates in a complex chemical equilibrium. Most of the ocean's dissolved inorganic carbon exists as bicarbonate and carbonate ions. When carbon dioxide dissolves in seawater, it reacts with water to form carbonic acid, which then dissociates into these ions. This chemical buffering system allows the ocean to hold far more carbon than it could if it were only stored as a dissolved gas. It plays a major role in determining the overall alkalinity and pH of the global marine environment. The precise balance of these carbon species is a function of temperature, alkalinity, and the partial pressure of carbon dioxide in the overlying atmosphere. Colder water can hold more dissolved carbon dioxide, which is why polar oceans are particularly effective at absorbing this gas. Alkalinity, a measure of the water's ability to neutralize acid, is influenced by the weathering of rocks on land and the dissolution of calcium carbonate shells in the ocean. Together, these variables determine what's called the saturation state of the ocean, which dictates whether minerals like aragonite and calcite, used by many marine organisms to build shells, will form or dissolve. By absorbing approximately 30% of the carbon dioxide emitted by human activities, the ocean has significantly mitigated the rate of atmospheric warming. It's been a crucial buffer, slowing the pace of climate change. However, this service comes at a chemical cost. As the ocean takes up more carbon dioxide, the concentration of hydrogen ions increases, which leads to a decrease in the water's pH. This shift in chemistry is known as ocean acidification, and it's occurring at a rate faster than at any time in the last several million years. The ocean is becoming more acidic, and that has consequences. Ocean acidification poses a direct threat to calcifying organisms, organisms that build shells or skeletons out of calcium carbonate. This includes corals, mollusks, and certain types of plankton, like coccolithophores. As the water becomes more acidic and the concentration of carbonate ions drops, it becomes more energetically difficult for these animals to build and maintain their calcium carbonate structures. It's like trying to build a sandcastle while the tide is coming in. In extreme cases, the water can become corrosive enough to actively dissolve existing shells and reef frameworks. Because these organisms form the foundation of many marine food webs. Coral reefs support a quarter of all marine species, and tiny calcifying plankton are eaten by everything from small fish to whales. The chemical shift of the ocean has the potential to cause cascading effects throughout the entire global ecosystem. The ocean floor serves as a vast geological archive, accumulating various types of sediments that tell the history of the planet. These deposits are generally categorized by their origin. Terrigenous sediments consist of fine clays and silts weathered from continental rocks and transported to the sea by rivers and wind. Biogenic sediments are formed from the hard remains of marine organisms. There are also contributions from volcanic ash, from eruptions, and even cosmic dust from space, which settle through the water column to eventually rest on the abyssal plains. All of this accumulates layer by layer, year by year, recording the passage of time. Calcareous ooze is a widespread biogenic sediment found in relatively shallow to mid-depth ocean regions. It's primarily composed of the calcium carbonate shells or tests of microscopic organisms such as foraminifera and coccolithophores. These organisms thrive in the sunlit surface layers, and upon their death, their skeletal remains rain down onto the sea floor. However, calcium carbonate dissolves more readily in the cold, high-pressure, acidic waters of the deep sea. There's a depth called the calcite compensation depth, or CCD, below which calcium carbonate dissolves faster than it accumulates. Calcareous oozes are typically found only on elevated features like mid-ocean ridges or plateaus that sit above this depth. In deeper or colder regions where calcium carbonate cannot persist, the seafloor is often covered by siliceous ooze. This sediment is composed of the remains of organisms that secrete shells made of silica, such as diatoms, which are photosynthetic algae, and radiolarians, which are predatory protists. Silica is much more resistant to dissolution in deep acidic waters than calcium carbonate. Consequently, siliceous oozes are frequently found in areas of high biological productivity, such as the Southern Ocean or equatorial upwelling zones, where these glass-shelled organisms flourish in the surface waters. The layered accumulation of these deep-sea sediments provides a high-resolution record of Earth's paleoclimate and oceanographic history. By analyzing the chemical composition and species diversity within sediment cores, long cylinders of sediment extracted from the seafloor, scientists can reconstruct past sea surface temperatures, fluctuations in global ice volume, and shifts in major ocean currents. For instance, the ratio of oxygen isotopes found in the shells of buried foraminifera serves as a proxy for ancient global temperatures and sea levels. Different isotopes of oxygen are incorporated into shells at different rates depending on the temperature of the water. By measuring these ratios, researchers can track the onset and retreat of ice ages over millions of years. It's like reading the rings of a tree, but on a planetary scale. Seamounts are prominent underwater mountains that rise at least 1,000 meters above the surrounding seafloor, but remain submerged beneath the surface. They're incredibly numerous. Estimates suggest there are tens of thousands of them throughout the global ocean. Most seamounts originate as volcanic features formed over hotspots, places where plumes of hot mantle material rise to create volcanoes, or near mid-ocean ridges. Because they provide a hard substrate in an otherwise sediment-covered abyss, they act as biological magnets, attracting a high diversity of life. They often host unique endemic species that are found nowhere else on Earth. The volcanic nature of seamounts means that even after their eruptive phase ends, they continue to influence the deep-sea environment. Their steep slopes deflect deep ocean currents, causing localized upwelling that brings nutrient-rich water toward the summit. This creates a productive oasis in the open ocean, supporting dense populations of deep-sea corals, sponges, and commercially valuable fish. Because these communities are often isolated from one another by vast stretches of flat abyssal plain, each seamount can evolve its own distinct biological character. It's like an island in the sky for terrestrial life, isolated, unique, fragile. Part 4. Guyots represent a specific stage in the life cycle of oceanic volcanoes. These are flat-topped seamounts that were once active volcanic islands poking above the ocean surface. Picture a volcanic island in its prime, perhaps covered in vegetation, surrounded by coral reefs. Over time, the combined forces of wave erosion and the gradual cooling and contraction of the underlying lithosphere, a process known as subsidence, caused the island to flatten and eventually sink below the waves. The waves wore down the peak, creating a flat summit, and as the volcanic rock cooled and the plate beneath it moved away from the heat source, the entire structure slowly subsided, descending beneath the surface. The flat summits of Guyos are often covered in ancient reef deposits or sediments, providing a clear record of this geological transition from a sunlit island to a submerged, flat-topped mountain. The coastal zone is the most dynamic interface on the planet. It represents a high-energy transition where marine and terrestrial processes continuously collide. This narrow band of the Earth's surface includes a diverse array of landforms, from eroding rocky cliffs and sandy beaches to complex depositional systems like estuaries and deltas. The morphology of these regions is never static. It's shaped by the relentless work of waves, tides, and currents, as well as the input of sediment from inland rivers. Because these areas are subject to both terrestrial weather and oceanic energy, they're among the most rapidly changing landscapes on Earth. A beach you knew as a child might look completely different today, reshaped by storms, altered by currents. Tides represent the most predictable pulse of the ocean, a periodic rise and fall of sea level driven by the gravitational interaction between the Earth, the Moon, and the Sun. As the Earth rotates, different regions pass through the gravitational bulges created by these celestial bodies, resulting in the rhythmic advance and retreat of the shoreline. While the Moon exerts the primary influence due to its proximity, the Sun's position relative to the Moon dictates the intensity of the tides. When they align during new and full moons, their gravitational forces combine to create spring tides, with the highest highs and lowest lows. When they're at right angles to each other during the first and third quarters, their forces partially cancel out, creating neap tides, which are less extreme. The vertical distance between high and low tide, known as the tidal range, is not uniform across the globe. It's profoundly influenced by the geometry of the coastline and the depth of the sea floor. In the open ocean, far from land, the tidal range may be less than a meter, barely noticeable. But when tidal waves enter funnel-shaped bays or narrow channels, the water is compressed and forced upward. This can result in extreme tidal ranges. In the Bay of Fundy, on the border between New Brunswick and Nova Scotia, the water level can fluctuate by over 16 meters in a single cycle. Imagine a 3-story building appearing and disappearing beneath the waves twice a day. These movements drive powerful tidal currents that move massive volumes of water and sediment in and out of coastal basins, creating dynamic environments where conditions change dramatically every 6 hours. Ocean waves are the primary vehicles for energy transport across the sea surface. They're generated as wind friction transfers kinetic energy to the water. The eventual size and power of these waves are determined by 3 factors: wind speed, the duration the wind blows, and what's called the fetch, the distance of open water over which the wind travels. A gentle breeze blowing for a few minutes over a small lake creates ripples. A hurricane blowing for days over 1,000 miles of open ocean creates towering waves. In the open ocean, waves move as pulses of energy. The water molecules themselves don't travel forward with the wave. Instead, they move in circular orbits, rising and falling as the wave passes. This energy can travel thousands of miles from a distant storm, remaining largely invisible, the waves long and rolling and smooth. It's only when they interact with the shoreline that their true power becomes apparent. As waves transition from deep to shallow water, they begin to feel the bottom. The circular motion of the water molecules becomes elliptical and flattened. Friction with the seafloor slows the base of the wave, while the crest continues at its original speed. As a result, the wave shortens in wavelength and increases in height, becoming increasingly unstable. Eventually, the top of the wave outruns the base and collapses, transforming into surf. This breaking process releases the energy accumulated over perhaps thousands of miles directly onto the beach or cliff face. It's no wonder the coast is such a dynamic place. When waves strike the shore at an angle rather than head-on, they generate a longshore current that flows parallel to the coastline. This current acts as a submerged conveyor belt, transporting vast quantities of sand and sediment along the shore in a process called longshore drift. Over time, this movement can significantly reshape the coast, creating features like sand spits, narrow fingers of sand extending from the shore, and baymouth bars that can close off bays. It can strip sand from one beach, leaving it eroded and rocky, only to deposit it on another, building it up. Human interventions, such as jetties or groins built to trap sand or protect harbors, often disrupt this natural flow, leading to unintended erosion or sediment buildup elsewhere. The ocean, in a sense, tries to maintain its equilibrium, and when we interfere, there are consequences downstream. Estuaries are critical transition zones where the fresh water of terrestrial rivers meets and mingles with the salt water of the sea. These are semi-enclosed bodies of water, places like Chesapeake Bay, San Francisco Bay, the Thames Estuary. They're highly productive because they trap nutrients from both land and ocean. Because salt water is denser than fresh water, it often slides along the bottom in what's called a salt wedge, while the lighter fresh water flows across the top. This creates a layered, stratified system. This interaction creates a complex, brackish environment that serves as a vital nursery for many marine species, providing abundant food and protection from the high-energy environment of the open coast. Many fish and crustaceans spawn in estuaries, using them as safe havens for their young. The salinity within an estuary typically follows a distinct horizontal and vertical gradient. Near the river mouth, upstream, the water remains nearly fresh. But as you move toward the sea, the salinity gradually increases to match that of the open ocean. This gradient is highly sensitive to the tides and seasonal river flow. During high tide or periods of drought, the salt front moves further inland. Heavy rains can push the freshwater plume far out into the coastal ocean. This fluctuating chemistry requires the organisms living here to possess specialized physiological adaptations to handle rapid changes in salt concentration. It's not an easy place to live, but for those that can tolerate it, it's incredibly rich. Coastal wetlands, such as salt marshes in temperate zones and mangrove forests in the tropics, serve as the planet's natural shock absorbers. These ecosystems are dominated by salt-tolerant vegetation, grasses in marshes, trees in mangroves, that stabilizes the shoreline by trapping sediment with their complex root systems. By dissipating the energy of storm surges and waves, these wetlands protect inland areas from flooding and erosion. During a hurricane, the difference between having a healthy coastal wetland and not having one can be measured in lives and property. Furthermore, these wetlands are highly efficient carbon sinks, sequestering large amounts of organic matter in their waterlogged, oxygen-poor soils. That carbon, instead of returning to the atmosphere, is locked away in the mud. Barrier islands are elongated, narrow accumulations of sand that sit parallel to the main coastline, separated from it by lagoons or marshes. The Outer Banks of North Carolina, the Barrier Islands of Texas, the islands along the coast of the Netherlands. These are incredibly transient features. They're shaped by the very storms they protect the mainland from. Through a process called overwash, storm waves push sand from the ocean side of the island to the landward side, causing the entire island to slowly migrate toward the shore over decades. It's like the island is rolling over itself, moving inland. Because they're composed of loose sediment, barrier islands are highly susceptible to sea level rise and changing current patterns, making them some of the most vulnerable landforms in the coastal system. The surface of the ocean is not a perfectly flat or level plain. It has topography, a complex landscape of hills and valleys. These subtle variations in height, often measuring only centimeters or a few meters across thousands of kilometers, are the result of several physical forces acting in concert. Large-scale currents cause water to pile up in certain regions due to the Coriolis effect. Differences in water temperature lead to thermal expansion. Warmer water occupies more volume and thus sits higher. Additionally, variations in Earth's gravitational field, dictated by the uneven distribution of mass in the underlying crust, create permanent undulations in the sea surface. There are places where the ocean is literally higher than in others, held there by gravity. To map this invisible landscape, scientists utilize satellite altimetry, a technology that measures the time it takes for a radar pulse to travel from a satellite to the ocean surface and back. By calculating the precise distance between the satellite and the water, researchers can detect minute changes in sea surface height. These measurements reveal the presence of underlying circulation patterns that are not visible to the naked eye, such as the circular mounds of water at the center of oceanic gyres, or the depressions associated with powerful, fast-moving currents. It's like being able to see the currents from space by looking at the shape of the sea surface itself. Among the most dynamic features identified by satellite data are mesoscale eddies. These are massive rotating weather systems of the sea, typically spanning tens to hundreds of kilometers in diameter. Eddies are often pinched off from major boundary currents like the Gulf Stream. A meander in the current becomes unstable and breaks away, forming a rotating ring of water. These eddies trap a core of water with distinct temperature and salinity characteristics within their centers. As they drift across ocean basins, slowly spinning, slowly dissipating, these rotating water masses act as mobile capsules, transporting heat, salt, and entire communities of plankton and fish far from their points of origin. They significantly influence regional climates and biodiversity. When two water masses with different physical properties meet, they form a boundary known as an ocean front. Similar to atmospheric weather fronts, these oceanic transitions are characterized by sharp gradients in temperature, salinity, or nutrient concentration. Fronts are often zones of intense physical energy where water masses converge, forcing nutrient-rich water to rise or causing organic matter to accumulate. This concentration of resources makes fronts biological hotspots, attracting vast numbers of phytoplankton, which in turn draw in higher predators like tuna, whales, and seabirds. If you were to fly over an ocean front, you might see flocks of birds wheeling and diving, drawn to the abundance below. While waves on the surface are familiar to anyone who's been to the beach, the ocean also hosts internal waves that propagate along density interfaces deep beneath the surface, such as the thermocline. These waves are triggered when tidal currents or winds push layers of different densities over underwater obstacles like seafloor ridges. Because the density difference between layers of water is much smaller than the difference between air and water, internal waves can reach massive amplitudes, sometimes exceeding 100 meters in height, while remaining virtually invisible from the surface. They're like ghost waves, moving through the ocean's interior. As they travel and eventually break against continental slopes, they facilitate the mixing of deep and shallow waters, helping to transport nutrients upward and heat downward. The vertical structure of the ocean is maintained by a constant struggle between stratification and turbulent mixing. Stratification wants to keep the ocean layered, with light, warm water on top and heavy, cold water below. Mixing is the process that prevents the ocean from becoming a stagnant, perfectly layered cake. It's driven by the energy of surface winds, the rhythmic friction of tides against the seafloor, and the breaking of internal waves. This turbulence is essential for the global climate because it carries heat from the sunlit surface into the deep interior and brings life-sustaining nutrients from the abyss back up to the surface, where they can be used by photosynthetic organisms. Each evening, the ocean witnesses a massive biological phenomenon known as diel vertical migration. Thousands of species of zooplankton, small fish, and cephalopods begin a synchronized ascent from the dark mesopelagic zone toward the surface. They move under the cover of darkness to feed on the abundant phytoplankton in the euphotic zone, while minimizing their risk of being seen by visual predators. As dawn approaches, this vast army of organisms retreats back into the cold, dark depths to remain hidden during the day. This happens every night in every ocean across the entire planet. This daily cycle is recognized as the largest migration of biomass on the planet, occurring every 24 hours. Beyond its scale, the migration serves a critical role in the carbon pump. By feeding at the surface and then descending to depth to excrete waste and respire, these migrating animals actively transport carbon from the atmosphere into the deep ocean. This biological shortcut bypasses the slower process of passive sinking, making the movement of these tiny creatures a significant factor in the Earth's overall carbon cycle. The geographic distribution of marine life is not random. It's strictly governed by environmental gradients. Organisms are sorted across the ocean based on their specific tolerances for temperature, hydrostatic pressure, light intensity, and dissolved oxygen. For example, some species are stenothermal, meaning they can only survive within a very narrow temperature range. Others, called euthermal, can tolerate a wide range. These gradients act as invisible barriers, defining the boundaries of marine provinces and determining which species can coexist in a particular volume of water. Advancements in genetic sequencing have revealed complex patterns of connectivity among these dispersed populations. Some marine species, particularly those with long-lived larval stages that drift on major currents, show high levels of genetic similarity across entire ocean basins. This indicates a well-connected metapopulation, where genes flow freely across thousands of miles. In contrast, other species exhibit deep genetic fractures, where populations separated by only a few hundred kilometers have become locally adapted to specific chemical or thermal conditions. These studies highlight the balance between the ocean's role as a highway for dispersal and its role as a driver of evolutionary divergence through isolation. The global ocean is not a uniform body of water. It's composed of distinct water masses, each characterized by a unique fingerprint of temperature and salinity. These properties are acquired at the surface through interaction with the atmosphere and remain remarkably stable once the water sinks and moves into the interior. By mapping these signatures, oceanographers can trace the movement of water across thousands of miles, identifying where a specific parcel of water originated, whether it was chilled by Antarctic winds or warmed in the Mediterranean, and how long it has been sequestered from the surface. It's like being able to read the water's history. Antarctic bottom water represents the densest water mass in the world's oceans. It forms primarily in the Weddell and Ross Seas, around the coast of Antarctica, where frigid air and the formation of sea ice create a brine so cold and salty that it plunges to the very bottom of the ocean floor. From there, it spreads northward, creeping along the sea floor into the deepest basins of the Atlantic, Indian, and Pacific Oceans. This massive, slow-moving layer of water is the primary source of oxygen and cold temperatures for the global abyss. It serves as the foundation of the ocean's vertical structure. In the northern hemisphere, North Atlantic deep water acts as a critical counterweight in the global circulation. This mass forms when relatively warm, salty water from the subtropics, carried north by the Gulf Stream, loses its heat to the cold Arctic atmosphere. As it cools, its high salinity makes it dense enough to sink in the Labrador and Greenland seas. This water mass then flows southward at intermediate depths, eventually crossing the equator. The formation of North Atlantic deep water is a primary driver of the conveyor belt, pulling more warm water northward and maintaining the temperate climates of northern Europe. Below the immediate surface, the ocean contains layers known as mode waters. These are relatively thick, homogeneous layers characterized by nearly uniform temperature and salinity. They form during the winter when intense cooling and wind-driven mixing penetrate deep into the water column, creating a large volume of water with consistent properties. Once the surface warms in the spring, these mode waters are capped and subducted into the interior of subtropical gyres. They serve as important reservoirs for dissolved gases and nutrients, moving horizontally across ocean basins just beneath the surface layer. The uppermost portion of the ocean is the surface mixed layer, a region where wind, waves, and convective cooling constantly stir the water. This turbulence creates a nearly uniform profile of temperature and salinity from the surface down to the top of the pycnocline. The depth of this layer is highly seasonal. In the summer, solar heating creates a buoyant, shallow, mixed layer. In the winter, fierce storms and cooling cause the layer to deepen significantly as it entrains colder water from below. This seasonal breathing of the mixed layer regulates the exchange of heat and gases between the atmosphere and the deep ocean. In polar regions, the formation of sea ice acts as a powerful salt pump. When seawater freezes, the crystal structure of the ice is composed of pure water, essentially squeezing out the dissolved salts into the remaining liquid. This process, brine rejection again, significantly increases the salinity and density of the surrounding water, causing it to sink and drive deep ocean circulation. Conversely, when sea ice melts during the summer, it releases a pulse of fresh water onto the surface. This creates a buoyant, low salinity lens that stabilizes the water column and can temporarily suppress the vertical mixing of nutrients. The relationship between the ocean and sea ice is a critical component of the Earth's albedo, or reflectivity. Bright white sea ice reflects the majority of incoming solar radiation back into space, keeping the polar regions cool. However, as ice melts and reveals the dark ocean surface below, the water absorbs more heat, leading to further melting in a process known as the ice albedo feedback. It's a positive feedback loop. Warming causes melting. Melting causes more warming. This interaction not only regulates global temperatures, but also dictates the habitat conditions for specialized polar species, from the microscopic algae living within the ice to the apex predators like polar bears that hunt upon its surface. The Southern Ocean is perhaps the most vital region for the global abyssal ocean, as it's the only place where deep waters from all major basins are brought to the surface to be ventilated and transformed. The intense winds and cold temperatures of the Antarctic circumpolar current facilitate the production of both Antarctic bottom water and sub-Antarctic mode water. These masses influence the chemical and thermal properties of the entire global seafloor, making the Southern Ocean a primary regulator of the planet's long-term climate stability. It's the lungs of the deep ocean, breathing in fresh air, exhaling old. Part 5. On a global scale, the ocean is the primary source of the water vapor that fuels the Earth's hydrological cycle. Solar energy evaporates water from the sea surface, leaving salts behind and lifting purified moisture into the atmosphere. This vapor eventually condenses into clouds and falls as precipitation over both land and sea. To close the loop, river runoff carries fresh water, terrestrial minerals, and organic matter back into the ocean basins. This continuous cycle not only redistributes fresh water across the continents, but also regulates the salinity and nutrient balance of the coastal oceans. It's a closed system, endlessly recycling, endlessly renewing. The exchange of heat and moisture at the ocean-atmosphere interface is a fundamental driver of global weather systems. The ocean acts as a giant thermal buffer. For example, the heat stored in the tropical Indian Ocean provides the energy for the seasonal monsoon winds that deliver water to billions of people in Asia. Without that stored ocean heat, the monsoons would fail, and the consequences would be catastrophic. Similarly, the development and intensification of tropical cyclones, hurricanes, typhoons, cyclones depending on where you are in the world, are fueled by the evaporation of warm surface waters. A hurricane is essentially a heat engine converting the thermal energy of the ocean into wind and rain. Because the ocean has such a high heat capacity, it provides a memory for the climate system, allowing weather patterns to be influenced by oceanic conditions that developed months or even years prior. What happens in the ocean today can affect the weather half a year from now, half a world away. Phenomena such as El Niño and La Niña, collectively known as the El Niño Southern Oscillation, or ENSO, demonstrate the profound link between ocean temperature and global climate. During an El Niño event, the usual trade winds weaken. Without those winds pushing water westward across the Pacific, warm water sloshes eastward, pooling along the coast of South America instead of remaining concentrated in the western Pacific. This shift alters the position of the jet stream, the high-altitude river of air that steers weather systems across the globe. The result? Dramatic changes in rainfall and temperature patterns worldwide, causing droughts in some regions and floods in others. Australia might experience severe drought. California might be inundated with rain. These events represent the most. To understand these complex systems, scientists rely on a global network of observing technology. One of the most successful systems is the Argo program, which consists of thousands of autonomous floats drifting throughout the world's oceans. These floats are remarkable pieces of engineering. They spend most of their time at a depth of 1,000 meters, drifting with the currents, silent and unseen. Occasionally, they dive to 2,000 meters before rising to the surface. When they reach the surface, they beam data on temperature and salinity to satellites overhead, then dive again to continue their journey. This provides a continuous, real-time view of the upper half of the global ocean, allowing researchers to monitor changes in ocean heat content and salinity with unprecedented precision. It's like having thousands of weather stations scattered across the sea, constantly reporting back. Beyond autonomous floats, oceanographic observing systems include moored buoys that provide long-term data at fixed locations. These buoys are anchored to the seafloor, sometimes in waters several kilometers deep, and they measure everything from wind speed to water temperature to wave height. Satellite altimetry monitors sea level rise and current speeds from space, giving us a bird's-eye view of the ocean's surface. Research vessels still play a critical role, conducting detailed surveys of ocean chemistry and biology that sensors cannot yet perform. Scientists lower instruments into the water, collect samples, observe life firsthand. Together, these tools allow researchers to track the ocean's response to climate change, the health of marine ecosystems, and the shifting patterns of the global conveyor belt. Despite these advancements, despite decades of study and billions of dollars invested in technology, much of the deep ocean remains unmapped and unexplored. We have better maps of the surface of Mars than we do of the ocean floor. Ongoing research continues to uncover new species, new chemical processes, and new geological features in what is often called the final frontier of our planet. There are mountains we've never seen, trenches we've never plumbed, creatures we've never encountered. The ocean holds secrets still, wonders waiting to be discovered. And that brings us to the end of our journey tonight. We've traveled from the sunlit surface to the deepest trenches. We've explored currents that circle the globe and ecosystems sustained by the Earth's inner fire. We've considered the chemistry that makes seawater salty, the physics that drives waves and tides, the biology that fills every corner of this vast realm with life. The ocean is not just a backdrop to our existence. It's not just scenery. It's the engine that powers the planet, the lungs that provide half our oxygen, the thermostat that regulates our climate. It's easy to forget, living on land, that we're inhabitants of a water world. But we are. The Earth is fundamentally a marine planet, and understanding the ocean is understanding our home. Thank you for spending this time with the Curious Owl tonight. I hope this exploration has brought you some measure of peace, some quiet wonder at the complexity and beauty of our world. If you found value in this journey, perhaps you'll return for another. And if there's something you'd like to share, a thought, a suggestion, something that could make these explorations even better, please leave a comment. Your voice matters. For now, rest easy. Let the gentle rhythm of the ocean's pulse carry you into sleep. The tides will continue to rise and fall. The currents will continue to flow. The great cycles of the sea will turn, as they have for billions of years, as they will for billions more. Good night.